Well, thank you very much, Caroline, and to CIRMMT members generally for inviting me here to give this talk and the really interesting workshop that we had this morning. And thank you to the workshop presenters as well. There's some really, really cool stuff that's happening here. Really excited to see the kinds of things going on around the center. So I'm going to talk this evening about digital musical instruments and also some of both the cultural factors and the technical factors that go into making them. I'll start with just a bit of context about where I come from. I'll talk about some of the projects that I've made, and I'll conclude with maybe some more general questions about what it is that we're doing when we create new music technologies. So as Caroline said, I lead the Augmented Instruments Laboratory, which is part of the Center for Digital Music at Queen Mary. And this is a team currently composed of 12 PhD students and postdocs, a really talented group of artists, technologists, researchers doing a whole variety of different work all around the intersection between music and performance and technology. And if you want to know more about what goes on in the lab, you can have a look at the lab website, instrumentslab.org. There's a list of publications and more information about the various projects that we're working on at the moment. Now this talk is, as I said, about musical instruments. And this very term, instrument, I think hides enormous complexity. Because to the engineer, the musical instrument could be seen as a transducer, something that converts the performer's actions into sounds. On the other hand, to somebody working in music psychology, the instrument could act as an extension of the performer's mind and body, mediating their sensing and their action. But to the ethnomusicologist, a musical instrument is a product of a specific social and cultural context. And all of these different views coexist, and I'm going to talk about each of them in turn in this talk. Just to start out with, the engineering view of musical instruments. This is extremely important if we want to create high-quality performance technologies. And there's this quote that I really like from Bill Buxton, one of the pioneers of human-computer interaction, talking about the three levels of design. You have your standard spec, you have your military spec, and you have your artist spec, and that the third of these is the hardest and the most important. Apparently, if you can nail that, then military technologies become easy, but that is not the reason that we do this. That's not the reason that I'm here today. But there is a really important point here, which is that it's trivial these days to make a digital system that produces some sounds in response to a performer's actions. But if you want to make something that a professional performer who spends years of their life devoted to learning an instrument is willing to take on a stage and play with, this is a very different kind of challenge. Some of the challenges include the level of spatial and temporal precision that's required, micrometer scales, very low latencies. You have the fact that most musical instruments involve quite a large number of degrees of freedom. The fact that there are multiple modalities involved, not just sound, but oftentimes tactile feedback as well. On an acoustic musical instrument, the entire instrument might be a sensing surface, not just a few buttons or controls. Everything can be highly nonlinear, which to a scientist or engineer makes your problems much, much, much more difficult. And then, if all of that wasn't enough, everything needs to be 100% reliable if somebody is willing to take it on stage and perform. And if that wasn't enough, then you also have to consider that no performer is a blank slate. You have human skills, you have expectations that need to be met in order for this to be something that somebody can make music with. Now, I just want to dig into some of these challenges a little bit more. And one of the places that we've made incredible strides in the past 20 years is around the mathematical modeling of musical instrument sounds. So we can build a model at this point that will simulate a piano or a violin or a drum head, oftentimes with quite a lot of precision. And we can even run this on a big bank of GPUs, potentially get it running in real time with enough computation. And yet, we still have a problem. The problem is this one. It's around the richness of interaction. What do we do about this interface between the performer and the instrument? The things that go on in the fingertips. And there's such an extraordinary amount of nuance that happens in most instruments at this physical and digital interface. And yet, with these physical models, oftentimes what we end up with to control them is something more like this. And you have this sort of, this kind of world that's trapped inside of a glass bottle with only the tiniest little hole to sort of peek in and see what's going on. In other words, one of the big technical challenges still facing us in digital musical instrument design is the integration of the physical and the digital elements. Looking next then at the view of the instrument as a mediator, a quote that I really like comes from Luke Nyes, who writes around embodied music cognition, talking about how the instrument comes to be an extension of the body, that a musician no longer experiences a boundary between herself and the instrument. This matches my own experience. I'm a string player, I play the viola, and I find that at a certain point you can stop thinking about the instrument, and you're still aware that it's there, of course, but that your attention can shift beyond the mechanics of operating the bow and the fingerboard towards some sort of higher level goal of the music that you want to make. And this phenomenon is not one that emerges overnight when you encounter a new instrument. It's something that depends on sensorimotor skills, which are developed over a long period of time. So we'll come back and talk about that in a moment. Finally, we have the instrument as a product of a social and a cultural context. Simon Waters writes about musical instruments as not being objects at all, but rather a process, a dynamic system in a constant state of change, seasoning, adjustment, and decay. The idea here is that musical instruments can really only be understood in relation to a broader cultural context, and the kind of ways that they're understood by performers, composers, audiences, and a number of other stakeholders. So this is the kind of overview of the different views of instruments. Now, before getting into any specifics of what work I've done, it's maybe worth asking a more foundational question, which is this one. Do we really need any more instruments at all? I mean, we have in 2004 Sergio Jorda saying, many new instruments are being invented and too little striking music is being made with them. In the nearly 20 years since this was written, I don't think the situation has changed much. Fundamentally, it's easier to build an instrument than it is to learn to play it. And we have this problem of kind of a perpetual cycling of technologies, and to an extent that we can't keep up with the skills that we need to really play them. Now, rather than asking what's wrong with new instruments, because maybe nothing is wrong, let me ask instead, what is it about old instruments that makes them so enduring? Why is it that we're still making music on these wooden boxes with strings and horsehair bows 500 years later? And there's lots of different reasons for this. One of them is that it takes a very long time to learn to play an instrument. Who's going to repeat that from scratch with something that is brand new? You have your virtuoso performers. They can serve as role models for new people to pick up an instrument. Established instruments also have bodies of repertoire that can motivate people to learn them. I mean, how many people learn to play guitar in order to play particular songs that they know and like? And then also, established instruments also have schools of pedagogy around them, so that there are kind of well-known and well-developed ways of learning instruments. Now, we could broadly classify these factors into two categories. One of them is around sensorimotor skill. This is fundamentally an individual phenomenon. It has to do with various kinds of psychological or neuroscientific processes around skill learning. And then the rest of it we can kind of lump into this category that we might call musical culture, which is a collective rather than an individual phenomenon. To distill that down to a shorter point, we could say that musical instrument design is not about the technology, or at least not primarily about the technology. It's about the performers, and it's about the culture. And what follows on from that is my suggestion that existing musical practice can be a valuable resource for designing new instruments. Now, by this I don't necessarily mean that we should just be building digital pianos and emulations of traditional stuff for all time, but rather some real richness can emerge from having one foot in a long tradition and another foot in something new and unfamiliar. One way of doing this, although far from the only way, is the idea of the augmented instrument. The name of my lab follows this idea, and I know that there are many people here who are working on augmented instruments as well. Essentially, an augmented instrument is literally a familiar instrument of some sort, plus more. So, hypothetically, if this blue circle is the space of techniques that you could play on your traditional instrument, the ideal augmented instrument would give you all of those things, plus an additional space of new creative techniques. Now, in reality, you can never add things without taking something away, however subtle or non-obvious that might be. So you end up with something a little bit more like this. But the idea is to maximize the creative novelty and minimize the amount that you might lose by doing this. I'll show you one example of an augmented instrument that I've built. And this is actually the very first digital musical instrument that kind of got me on this whole path that leads me to be here today. The instrument is called the magnetic resonator piano. The reason for the long name is that it is literally an acoustic grand piano, but more than that, because inside the piano are these electromagnets. They hang on brackets just above the strings, and they can induce vibrations in the strings even without the strings being struck by the piano hammers. Now, an instrument needs a way to play it, and in this case, the way to play it is through a sensor that goes on the piano keyboard. It measures the continuous position of each of the keys, and the reason that's important is something I'll come back to. And then finally, digital instruments typically involve some form of relationship or mapping between what the performer does as sensed by some kind of sensor elements and what kind of sound is ultimately synthesized. And so there's a mapping between what happens at the keyboard and what happens inside the piano. And the fine-tuning of this was really important to the character of the instrument. I'll play a short video now just to give you an idea of what this sounds like, and then we can talk more about how it works. All right, so that's an example of the sound world of the instrument. Let's talk about how that happened. The basic technical principle is this one. Piano strings are made out of steel. Steel is what's known as a ferromagnetic material. That means that you can basically pull on it with a magnet. And it's not that interesting to put a permanent magnet inside a piano. It doesn't sound like anything. But what is interesting is to put an electromagnet inside the piano, because when you run the current through the electromagnet, it pulls the string up very slightly toward the magnet. You can then turn the current off, the string is allowed to go back down, and you can switch it on and off at the fundamental frequency of the string or at one of its harmonics, and you can induce vibrations into the strings. And by changing the characteristic of the waveform that you put into the magnet, you get different pitches, amplitudes, timbres, etc. Um, this idea of modulating a string magnetically, of course, goes back many, many decades. You may have seen it in the context of the EBow for electric guitar. A lot of people have seen these little devices which use a kind of feedback loop to keep the string ringing. There's also a number of other projects that actually use electromagnets inside a piano. Alvin Lucier has a piece doing precisely that. But there are a number of different ways to construct an instrument out of this principle. And I'll show you the way that I've done it mechanically, first of all. Here we have one electromagnet for each note of the piano, so potentially up to 88 of them. And there are a custom set of amplifier boards which basically route signals from the computer audio interface to the corresponding amplifier, which then drives the corresponding magnet. I have some papers that talk about the technology of this, which I'm happy to point you to afterwards if you're interested. A close-up view of the magnets is here. You can see that the magnets do not touch the strings. They need to be able to ring. Instead, they hang about 1 to 3 millimeters above the strings to get basically as close as possible until you end up with contact between them. Now, this is probably the most visually striking aspect of the instrument, but I would actually stake the claim that the identity of this instrument, what makes it different than the other electromagnetic pianos that are out there, is actually more in the keyboard and in the mapping than it is just in the magnets. And I'll tell you why. It's because what you get from the electromagnets is the ability to continuously shape each one of the notes. Again, I told you I'm a string player. I'm used to the idea that with the bow, I can modulate the sound of any note in a number of different facets at the same time. And the magnets let me do that, but if all I have is a MIDI keyboard, well, note on, note off, you're back to the percussion problem. And of course, MIDI, you can have controllers on the top of your keyboard, you can have aftertouch, there's a lot of things that you can do. But is there a way that from the acoustic piano keyboard, we could have a richer gestural language that would somehow translate to the nuance of what these magnets do? That's what I tried to do. The way that I approached the problem started from a device called the Moog piano bar. This was a product that was made by Moog Music in the early 2000s, a MIDI scanner for the acoustic piano. Basically, you take this big bar and you drop it at the back of the keyboard, and it gives you MIDI data. You press the keys and you get your note velocities, note on, note off. And the way it works is with optical sensing, reflections off the white keys to measure the position, and a little kind of beam interruption sensor across the black keys. Now, MIDI doesn't solve the problem though. So can we do better? And it turns out, yes. It turns out that if you crack open the case there, and you go poking around inside this device, you can get the raw optical signals that come out of the scanner. And this is really useful, because instead of what you see on the left, note on, note off, you can get for one note what you see on the right, which is this amazingly rich picture of key position over time, which can show you all sorts of little details. Like in this case, for example, you see the rounded top on that blue plot. That's because when I pressed the key, I pressed into it when it got to the bottom of the key bed. There's felt at the bottom of the key bed, so it moves a little bit. So you kind of get a key pressure reading. Or on the bottom, you have the velocity of the key during the very short period when the key is moving. And the fact that that velocity is increasing steadily and then stopping shows that it was a press touch as opposed to a struck touch where a moving finger encounters the key. So you can actually learn a lot of things about piano technique entirely apart from electromagnets here as well. But it also lets you add extended techniques like little taps in the key surface or vibratos or halfway key presses. And these can be used as musical resources. Now, one problem that I've had as this project has gone on is that I've wanted to make more magnetic resonator pianos, and the scarcity of the piano bar and the kind of fiddliness of that modification really get in the way. So I've designed, together with Giulio Moro, who was a former PhD student in the lab, we have made a new keyboard scanner, which replicates all of this, but is natively designed for continuous key position. So, tech specs here for your consumption. And one convenient practical aspect of this is that it folds in half when you want to transport it, because the piano bar is just really a big thing to get into your luggage. So happy to talk more about that afterwards if you're interested in knowing more about it. We'll now just talk about the mapping between what happens at the keyboard and what happens inside the piano. This is something that I finalized actually quite a number of years ago, and it stayed more or less the same, so that the instrument could develop an identity of its own. But the basic idea is this. The MRP is designed to be an instrument in a traditional sense, that you do something and you hear something in response. It could be programmatically played so that you pressed a button and you got a whole sequence of different notes. But that wasn't what I was after. Instead, the idea was essentially one gesture produces one musical event. And that led to three goals, which are somewhat in conflict. Let's keep everything from traditional piano technique, let's add some new techniques for continuous note shaping, and let's have the whole thing be no harder to play than the original instrument ever was. It becomes a balance between these three factors, and the principles are basically simultaneous execution of the new and the old techniques, and something that I would describe as sort of normal gestures produce normal sounds and weird gestures produce weird sounds, and you probably heard some of those things in the video. The point is this, augmentation is not free. You can add new things, but you're always going to take something away. And the goal, therefore, as I said earlier, is to maximize the creative novelty while minimizing the kind of relearning and unfamiliarity that comes out of it. So in this case, if here is our circle of piano techniques, we get lots of new things, different ways of changing, pitch, volume, timbre, that kind of thing. But at certain costs. For example, holding a note down with a key is going to produce a different kind of sustain than holding the note down with a pedal. Or you need to choose whether or not you're going to engage the resonator sounds. And that some of these new techniques are going to be unfamiliar. So, new sounds, but with some cost. Now, the sort of postscript to all of this is that whatever I think I was doing in making this instrument, the composers and the performers who encounter it are going to have very different ideas about what they're looking for. And Thor Magnusson writes really eloquently about this topic. He talks about how instrument makers actively design affordances, basically the things that you can do, whereas performers learning an instrument are more in the process of kind of exploring the constraints. How far can I push this? Would it do that? What happens if I ... And so let me show you a little video of a performance by Xenia Pestova-Bennett, who has become kind of one of the primary advocates of this instrument. Really fantastic performer, improviser, composer, and also a CIRMMT alum, who has made this piece for the instrument called Glowing Radioactive Elements. I'll play about 30 to 60 seconds of this and tell you what was going on. What on earth just happened there? Now, Xenia has this incredible way of encountering the instrument and kind of looking for the little seams to kind of pull apart, or the sort of little gaps to sort of fit into. And what she discovered is that when you hold the keys down just slightly, so you're at exactly the kind of point between off and on, you end up with this really funny interaction where the kind of noise on the scanner, electrical noise, translates through various kinds of slightly wonky and buggy software to switch between different states really rapidly to produce this glitchy waveform that goes into the magnets, where they're driving strings where the dampers have just barely begun to lift, so the strings are partly muted but partly not. And the result is these kind of crunchy, scratchy, strange sounds. Now, what's interesting and frustrating in equal measure is that if I want to make more instruments, if any aspect of this system changes, those effects are going to disappear. It's an accident, it's a byproduct of the design. And yet, we now have a repertoire that depends on it. And so, I'm going to find myself in the situation of emulating my own failures in the future so that I can be sure that this piece can be played. But of course, that emulation will be broken in its own way, and the next performer will come along and do something different with that. And so it goes. But that's I think that's part of the richness of this whole space of designing instruments. Anyway, that's the magnetic resonator piano. Let's step back again, though, to this question of sensory motor skill versus cultural context. And let's talk about it in the context of this very iconic instrument, the guitar. And I undertook a series of studies, together with a few of the members of my lab, around the idea of basically what would it mean to build a digital guitar-like instrument? What is the most important design factor for a digital guitar to be accepted? Now, you might think that this is obvious, but actually there's quite a number of factors at play. One of them is, well, if you want to build a guitar, there are probably some interaction modalities that suggest guitar playing, things like strings and frets and that kind of thing. On the other hand, this very object carries cultural significance, and quite a lot of it. And if I had chosen to put a Fender Stratocaster up here rather than this acoustic instrument, then we would have had a very different cultural association. And so I'm going to play for you now a series of 4 little videos that Jacob Harrison in my lab curated. If you've seen me talk before, you may have seen these videos before. But my question to you is, which of these 4 is the most guitar-like performance? And I'm going to ask for a show of hands at the end, so please watch. This is number 1.
Through the clouds, with a circus mind that's running wild. Butterfly.
Right. 4 different forms of sensory motor skill, by the way. So who says number 1 is the most guitar-like of these performances? Okay. All right, a few. Number 2? Ooh, a lot. Okay, number 3? Okay, a few. And who says number 4? Oh, yes, good. We have some people who say number 4. So the audience votes quite clearly for number 2, Alan Holdsworth. And I guess it's worth asking, kind of why is that? But what's interesting to me is that I've asked this question to a number of different audiences, and actually it comes back differently. I don't think I've ever seen an overall vote for number 4, but 1, 2, and 3 have all won that vote at different times. And I guess what it shows me is that the sort of idea of guitaring as an activity is something that far transcends the guitar as a physical object or a set of strings, and that there's so much kind of culture around this, and anything that we do as designers is going to have to enter this space somehow. So anyway, what did we do? Well, we did a few different studies with some design probes. We built a series of sort of kind of proto-guitars which had various forms. We had one that we had a pair of instruments where one of the pair had a little short lengths of string to play, whereas the other one used just a capacitive touch sensor to do exactly the same thing. And then we also had two instruments that were in a guitar-like body, compared with two instruments that were in little kind of tabletop forms. So basically 4 instruments and kind of 2 axes, if you will, the interaction modality and the physical form of the instrument. And we gave these instruments to different musicians, 16 people who were accomplished guitarists and 16 who identified as non-musicians. And we gave them a whole task, which I'm not going to go into. It basically involved improvising and accompanying a little folk melody, which I'll play for you right now. Sounded like this. Little postscript to that little tune was composed by an AI. That's from Bob Sturm's folk RNN work, which I encourage you to check out if you're interested. Really, really fascinating and well-motivated stuff. And basically what we did is each participant would get a pair of instruments. One of them we called a congruent pair, which was like the guitar with strings and the touch sensor in the tabletop. But the more interesting pair was the incongruent one, which was a sort of mismatch. The touch sensor guitar, or so I shouldn't give it away like that. I should say the touch sensor in the guitar body versus the strings in the tabletop. And I won't get into all the details. You should go read the paper. But basically, we asked loads of questions about which one was, kind of more guitar-like, and it turns out that basically nobody agrees. I don't know what that goes to show, except to say that the whole situation is really complicated. To be continued. We did also do one follow-up study that I found quite revealing. One of my kind of tropes as a designer was always what David Wessel calls control intimacy. Essentially the kind of nuance and detail that you can get out of an instrument. And this to me is like a kind of thing that's very near and dear to my heart in an instrument. So I always just assumed the best instruments are ones that have more detail. And we kind of asked, well, is that really true here? And the reason we could ask, in the case of this instrument that came to be known as Strummy, is that we could make 2 different versions of it. One of them, when you pluck those strings, it would trigger a sample. And the other version of it would just pass the signal from the pickup on that string into a physical model of, basically a Karplus strong model, a virtual model of a string. And so that preserves the entire kind of richness of detail of what you do on the strings. And I'll just show you what those 2 things sounded like. Gave these 2 instruments to the guitarists and to the non-musicians, and we basically just said, well, which setting do you like better and why? And what I would have assumed is that everyone would have been like, well, obviously the richer setting is the better one, because you can do so much more with it. And that turned out to be true for the guitarists. They basically universally said, yeah. The one that I can do more with, because it does more, it feels more like your knowledge of the guitar. But the non-musicians were really split, even tending toward preferring the less rich setting, because basically you didn't have to work as hard at it. You could sound pretty decent just starting out. And so it pointed to me a sort of a link up between sensory motor skill and the kind of preferred richness of interaction, which I think is really fertile ground for exploration of future instruments. Not something I'll get into here, but another thing I'd be happy to talk about later on. Just to say that the strummy has actually become a kind of ongoing stream of research in my lab by a number of different people. In addition to these studies, it's gone on to be used in the context of accessible digital musical instruments, working with people with learning disabilities and with various forms of motor impairments, and also has been used to explore various other concepts like this human-computer interaction notion of the research product, which is essentially as distinct from either a commercial product or a prototype, and then also been exploring notions of replication and reproducibility in digital instruments, which is, again, a theme that is also very important here at CIRMMT. So, so that's the strummy in a nutshell. Now, I'm going to come back here once more to talk about these different views of instruments, to make the point that these three different views of the instruments are entirely inseparable from one another, that the ecology of basically ultimately shapes the kinds of technology that we choose to make instruments. The technology that we use affects the sensory motor relationships that we have with instruments, and that in turn changes the musical ecologies that emerge from it. And this is not just a question of musical values, it's a question of technical values to begin with. To put it very succinctly, technology is neither good nor bad, nor is it neutral. Every technology carries certain kinds of values, and the technologies that we are choosing to build our instruments are telling us certain things. What are those things? Here I turn to my experience in teaching, actually. I teach classes on interaction design, making interactive systems, and also just to sort of the things that I see out there in the world. And you see some kinds of project ideas over and over again. Actually, Tom Igoe, who's one of the creators of processing, actually wrote a blog post about this, that it's very good. Physical computing's greatest hits and misses. And one of them, on the very top, is theremin-like interactions. Now, I don't here mean literally radio frequency antennas and waving your hands in the air necessarily. What I mean is this idea of XY mappings, that this direction is pitch and that direction is amplitude. It's such a natural thing to think about. You've got this number, you've got that number. Well, okay, we're going to assign them to this and that, and there we go, instrument done. And I guess more generally, what I'm interested in is that we make technologies, or we use technologies to make music, but we often should maybe ask the question, whose music is being encoded by this technology? By the tools we use and by the instruments that we build. In what contexts do we expect our instruments to be played? What aesthetic ideas are our instruments going to suggest to the performer? Back to Thor here for a minute. He talks about how instruments carry values, that the piano keyboard tells us that microtonality is of little importance, that the digital audio workstation will tell us it's totally reasonable to repeat the same little chunk of audio again and again and again, that kind of thing. I would go one step further. I would suggest that every technology that we use tells us certain things about what is reasonable to do. This object here, a force-sensing resistor, used in a musical context, is going to tell you certain things about what kinds of interactions you might want to have. You press on it, and there's other ways to go about interacting with this. Or this kind of style of code, Max or PD, gets us to think in certain ways about music. And I wrote a paper together with Koray Tahiroglu at Aalto University in Finland, where we kind of speculate that every computer music language has its own sound. And that's not because their oscillators and filters are implemented differently, but it's because they make you think in a different way, and that leads to different musical outcomes. Now, one way that this happens, and I think this can actually become a little bit problematic, especially for people starting out in the field, is a mentality that I would describe as design by analysis. And it goes something like this. I want to make an instrument to make music. Okay, that's what I tell myself. When I think making music, what I actually am thinking is one particular style of music, but I might not actually be totally aware myself of what I mean by music when I say that. But then what happens is I say, okay, I want to make music. Well, what are some concepts about music that I know? And what I really mean here is what words can I think of about music? I can think about, let's say that I want to make some classical piano music. Well, I can think of some words about that. We can talk about notes, pitches. We can talk about velocity or amplitude. Maybe we could talk about timing, or if I want to generalize this to MIDI, different voices, like different sort of strands of sound. Maybe I want to extend beyond the classical. I want to talk about timbre. I want to talk about spatialization. I want to control effects, whatever. Anyway, I've got a whole set of words, and I can put numbers on these words, and I end up with a dimension space. And the question is, does making music consist of navigating this dimension space? Analytically, maybe yes, actually. I could analyze a piece of music in terms of how it traverses the dimension space. Now here's the problem. The problem is that I next turn to my toolbox. Okay, let's go rummaging. Ooh, these are fun. I'm gonna take these parts out, and I've got this language that I'm used to working with, and what's gonna come out of all of this is a different set of numerical qualities based on these various sensors. And so what I'm gonna do is I'm gonna draw some sort of assignment between one dimension space and the other. And this, of course, is what we call mapping. Now, I'm not here to rag on mapping as a concept. As you can see, it's really important to my work. It's just that there has been a subtle shift that's happened here, a kind of inversion between analysis and synthesis. And it might be that even if I could analyze a piece of music in this space over here, that what I'm going to rig up with these sensors in this language is not going to easily get me back to making that kind of music once again. The upshot is that oftentimes there are particular kind of tropes and particular sounds that emerge from this process. And to query this, I worked with Giacomo Lepri, who is a recent PhD graduate of the lab, on a kind of compositional game. We had 3 sensors, and we had PD and Bella, which is a little embedded computing platform, which comes out of my lab. And we basically had them make super simple instruments, one sensor at a time, in pairs. If you want to know the details, it's in the paper. Instead, I'll just play you a couple little videos. So here are some examples of instruments where people had 10 minutes to make a simple instrument in PD using only a force sensing resistor. What does that sound like? I enjoy these, but I won't go through all of them. Why did we do this? What's the point? Well, some interesting things happened. One of them had to do with what people use to make sound. So in working with PD, people used various sound sources to generate the sound. They sine wave oscillators, phaser, which is a non-anti-aliased sawtooth, and white noise. And that was it. Although people would sometimes combine these, nobody used samples, nobody used wavetables, nobody used any other kind of sound sources. That was the comprehensive set of instruments, 28 people doing this project. Now, we also saw the way that people use the controls. The potentiometer mostly used for frequency, sometimes amplitude. FSR would be used for frequency or amplitude in roughly equal proportion. Buttons would be used as triggers, oftentimes as a kind of randomizer. Now, both pitch and amplitude are perceived on logarithmic scales, and yet 21 of these 26 instruments used linear scaling. That's, and why does that happen? Well, the other thing is that people came from all sorts of different musical backgrounds. They listened to all sorts of different music. They made all sorts of different music. But there's lots of things we never see. We don't see quantization to scales. We don't see samples. We don't see any patterns except regular metronomes, this kind of thing. And the question was, well, why not? What happened to all the other things that you could have done? Now, of course, they had 10 minutes. So I'm not proposing that these are the ideal instruments that anyone would have made with an arbitrary period of time. But the point is, PD makes certain things easier than others, and the things that are easier to do are going to happen more often. And by starting in that position, oftentimes that's going to have an influence that carries through all the way to the end. And it's not just technology, of course. There is a community of people who work in PD, and they're going to have an influence. The example patches are going to have an influence. But there is an influence of the technology. So there's this wonderful quote from Joe Snape and Georgina Bourne talking about how in a double bind, the technology that makes it possible for artists to forge unusual musical practices also locates those practices within familiar and consolidated technical and aesthetic universes. And I guess the point here is that any tool we use is going to carry certain values, and they're going to lead us certain places. And one thing that's important, I think, is not to let the kind of words and numbers about music take the place of the kind of experience of making it. But it's also just to realize that there's no free lunch. There's no ticket to kind of musical everything just by using the right tech. We need to realize the tech is going to lead us particular places. That brings me to basically the kind of little closing postscript of this talk. And it has to do, once again, with this little guy right here. And, of course, we're talking about that elephant in the music technology room, which is, well...
About 3 years ago, musical instrument manufacturers got together to decide on an interface system that would allow anybody's electronic musical instrument to connect to anyone else's. And they came up with MIDI.
MIDI, the standard that we love to hate, but which has had such a profound influence. So, okay, what's MIDI? Let's talk about that.
I'll just turn down the synthesizer so we can now only hear the piano. So what information can we send? I think the most important is key event information, which will tell the piano which notes I'm playing and when I'm playing them. And it will also send dynamic information, which is how hard I hit each note.
Right, so notice the value judgment sneaking in here. This is modeled on the keyboard. Key event information. When is the key hit and how hard? Now, let's go on.
So by using MIDI, up to 16 different instruments can be independently controlled because you assign each one a MIDI channel number. And this is really useful when they're to be played by a sequencer or a computer.
I love the contemporary sources, but hold everything for a second, though. I mean, notice what happened there. We went from key event information to you can control many different kinds of instruments, and if you look at general MIDI, trumpets and strings and what have you, but there's a sort of assumption somehow that we can reduce all of them to this particular, very reductive technical protocol that was oriented around the keyboard. The point is this, MIDI was adopted in the early 80s by a group of synthesizer companies with commercial as well as musical aims. They essentially just harmonize different companies' products with one another. And so it made loads of assumptions based on the technology of the time. Music is made of notes. We could really argue that point. That notes have discrete onsets and releases, very much arguable. And that they're organized 12 to the octave. And the point is that we are 40 years on from this now, and there's so much of popular music and all styles of music that have been inherited and been influenced by this set of assumptions. Who appointed these people the arbiters of all of music for the next 40 years? Well, nobody exactly, and yet, what they've done was so compelling, and it's traveled around the world with all sorts of unpredictable effects. Now, here we are in 2022. What are the big technologies out there? Well, AI is the big one, right? Of course, it's transforming everything. Embedded computing, I think, and these kind of miniaturized computers inside of everything is also changing everything. these technologies will be used to make music. They are being used to make music. And it's worth asking, by whom? For what ends and what values are going to be embedded? When we come back 40 years from now, what are we going to find out about the kind of music that was made because of the technologies that we have today? And that for me is kind of the next place that I'm going in my research. So I'm about to start a 5-year research project from the European Research Council, which is all around the kind of entanglement of culture and technology in making music, and asking about how engineering decisions can have aesthetic and even political consequences. And so this is basically watch this space. Hopefully I'll have something to report in a few years' time, and we'll see where it goes. But I'll wrap up there and just say, if you want to learn more about what's happening in the lab, there's the website, and I would be delighted to take a few questions as time permits. Thank you.